Saxon Advanced Mathematics, Lesson 76. I'm here to change your life today, students. We're beginning a topic of study called trig identities. These are a big deal in your future math career if you head down any sort of a path towards engineering or physics, or even just studying calculus. You will use trig identities. You already know some, but we're going to name them and start really thinking about them in a different way and using them in a different way. Trig identities are cool. They're like little snippets of information that we can use to solve puzzles. So let me start by showing you the ones that you already know. Then we're going to add a few more to the list. Then we're going to use them to solve some problems. So that's three main parts to this lesson. It's going to be a fairly long one, I believe. So what I want you to do right now is grab a fresh sheet of paper. There are so many of these identities. You're going to want to keep them separate from your other equations and formulas that you keep written down somewhere. I know you do. Grab a fresh piece of paper and I'll explain. Pause me if you need to. Okay, you're back with a piece of paper. What I'm going to do is show you, I'll show you here. This is a page I've filled out in previous years. This shows you a very strong structure of the different categories that we have. Don't worry about what they say right now. I just want you to notice the black is the different categories. And notice I have this all super structured so that you know how many there are of each kind. If there are a wider columns, then that helps you know how to fill those in. It's important that, well, it isn't important, but what I'll say is I've organized these in a way to try to make them easier for you to understand and to memorize. So if you don't want to use my format, you don't have to use my format, but I developed my format to help students understand and remember what the heck this is all about. So I'm going to go ahead and set them up the way I did right here as I go through with my notes with you. And I highly recommend that you copy my format. If you take tests with me, I'm going to have you fill out an identity page like that for our tests. And so it will be twice as convenient if you just start using that format now, because it will help you later. Okay, so draw some boxes with me. The first one needs to have 4 rows. I know I make mine bigger than you need to make yours. Okay, and then I'm going to divide the box in half about here, about 1/3 of the way across. That's a little more than 1/3, but you get the idea. This area we're calling the basic functions. You already know the basic trig functions. We know that sine, we put in theta as a placeholder for the angle. We used to write it without that when we were focused on learning just what the pairs were. We now are advanced enough that we always put the placeholder in of the theta. Okay, we have sine, cosine, and tangent, right? Those are our old friends. And we know that Oscar had a hold over Arthur. Okay, those are the basics. We've been doing those. I think it was lesson 43 of Algebra 2 that we have been working on those. So those should probably be pretty familiar to you. Then we learned something called reciprocal functions. And what we learned is that if you there's so many different ways to write this. If you take the sine of theta and put it over 1, we call that the cosecant of theta. If you put 1 over cosine, again, this is the reciprocal, right? We call this the secant of theta. And if you go 1 over the tangent of theta, that's called the cotangent of theta, right? And you can flip these around and write them the other way. You can say that, I'm going to run out of space. You can also say that the sine of theta equals 1 over the cosecant of theta. These are just different ways of saying that these two guys are reciprocals. Sorry, I ran out of space. Okay, so this is the way we learned them, that if you take 1 over the basic function, we have a new function with a special name, 1 over the basic, 1 over the basic. We can also state it the other way. We can say that the sine is equal to 1 over cosecant. So this is just algebra. We just changed their places and cross multiplying. When we start using these trig functions, sometimes it's helpful to see both options in front of your eyes because our head's going to be spinning with lots of other details. So I wrote the 2 different ways of stating the same thing just to try to make it easier for us in the long run. Okay, so we've already filled up the first section. The next section is one that you may have figured out on your own. Yeah, we've talked about it a little bit, but we're going to state it more overtly right now. This is called the quotient functions. Sometimes the name of these sound utterly crazy. Let's divide this box exactly in half. There's 2 versions of this. The tangent of theta, which we know is over Arthur, can also be written as sine of theta over the cosine of theta. That's another way we can create tangent. And then we can do cotangent. This I think is new. We flip them around. Makes sense, right? If cotangent is the reciprocal of tangent, then we take the ratio and we turn it upside down, right? Okay, so there are 3 different categories of trig identities that we've never called that before, but you've seen all of this before. None of that is new to you. I want to set up one more section and then we're going to step out of this page and talk about the details a little bit, but let's just get our chart organized. For the next piece of information, we need 4 rows in this one. And then we'll divide the bottom 3 rows right in half. And these are called they have 2 names. Running out of room again. These are called negative angle or even and odd functions, all right? And we're gonna fill these in just a few minutes. It'll look like this. What happens if you take the trig functions of the negative angle? All right, this doesn't make sense right now. Don't worry about that. I just want to set it up so that when we come back later, we'll be all ready to go. Okay, so we're going to figure out what all of this means in one hot minute. Okay, negative angles, right? That makes sense because we're finding what's the identity for the negative of all of these. Okay, this is your formula page for identity. Set that aside. We'll come back to that later. Let's take a look at these odd and even functions that we were talking about. We'll start with, let's start with cosine. That one's a little bit easier. And let's draw for ourselves just a basic sinusoid of the cosine function, all right? So this is y equals the cosine of x, okay? So we know that this is where the x-axis goes, this is where the y-axis goes. We're not doing anything fancy with the amplitude or the center line, so we can just call that 1 and minus 1. And we're not doing anything fancy with the periods or the phase angles. It's just a basic. Cosine, we know, starts at the max high, right? And then it goes down and up, and then we're going to do it in the negative direction as well. And I want to put the degrees on here because that's going to help us with what we're talking about. This is 0, so then we go minus 90, minus 180, minus 270. I hope you can see that. All right, and now we can connect the dots to make just a basic cosine curve. And what I'm hoping is that you're getting to the point where you can do this mentally. You can see this in your head. That will help you a lot keep this even and odd function thing straight. Look what happens with the cosine function. This is where the 0 degrees are, right? So we can think of this almost like, let's imagine we're folding this function up against itself with the fold right at 0 degrees, right? Fold here. What happens if we do that is we see that all of the curves on the two sides will match up, right? Because it's going to be right here. Then when we're 90 degrees out, it'll be the same as minus 90, right? They're both at 0. Then we go down to the low point. That's at 80 and negative 180. And then at 270 and minus 270, we're back up again. So when this one folds, it mirrors itself perfectly, and we say that cosine of x is an even function. All right, it's even because when you fold it, it works out perfectly, and the other way we can say that is the cosine of minus x equals the cosine of x. And let's just put in numbers to help us see if we believe it. We can use our unit circles. The cosine of negative 30 degrees should be equal to the cosine of 30 degrees. And if you have your unit circle handy, you can double check that. You'll find that they are both square root of 3 over 2. So our test works. So cosine is considered an even function because its negative angle is equal to its positive angle. Oh, now we're ready to fill this in on our other chart, right? I'll put this right here. I've got them, no, it's written in the same order. I used x's and here we've got thetas, same difference. The cosine of negative theta equals the cosine of theta. This is an even function, and I'll just give you spoilers right now that its reciprocal function behaves in the same way. Okay, so it doesn't matter if the angle is positive or negative, the cosine will be exactly the same. Okay, that's even angles. As you might guess, things are a little different when we look at the world of sine. Let's draw a quick and simple sine function. This is y equals the sine of, we'll say x again, just to make life complicated. There's y. We'll do the same thing. We're just going to graph it without any drama or complications. Okay, so we know that, let's do this again. Put the numbers in. This is minus 90 and this is minus 180. Okay, sine we know starts here at 0 degrees and it goes up and then down and back, right? It comes up out of 0 like so. So we can continue it back here. And then let's connect all these dots. Okay. Now, look what happens when we fold here. Okay, we're doing the very same thing as we did before. We're taking this function and we're folding it in half right on that 0 line, and we're looking to see how the points line up. In the sine function, they do not match up, do they? Positive 90 is the high value, negative 90 is the low value. So when we fold that, they're going to be opposites, aren't they? 180 and 180, okay, that's the same. But if we went out another point, and here, let me extend my curve just a little. This would be 270 minus. 270 is going to be the high point. Negative 270 is the high point. Positive 270 is the low point. So what we say is that, just I just want to see how I did this. The sine of x is an odd function. It does not line up, okay, perfectly like that. And we say that the sine of negative x equals minus the sine of x, right? Before we said plus, we said that they were the same. Here we're saying, no, actually they're different. If you want the sine of minus 90, you have to take the sine of 90 and then make it negative. All right, that seems a little weird. And we can prove it again. The sine of minus 30 degrees, if this is true, should be minus the sine of 30 degrees. See how I put that in there? The sine of minus 30 degrees is negative 1/2. And I'm going to put parentheses around here just to help you see it. We don't need them there. Minus, and what's the sine of 30 degrees? Positive 1/2. So it's true, it checks out when we actually use the numbers off our unit circle. To compare, we find that this relationship does hold true. So sine, like we said, is an odd function. He is an odd little boy. Okay, so we're going to add this. Sorry, wrong page. This is the one I want. So sine if we want the negative angle, then we take the positive angle and take the minus version of it. The reciprocal behaves the same way. And we have not looked at the sinusoid for tangent because it's complicated and weird. We'll get to it, but it's kind of a dead end. We don't use that a lot. But I will just tell you right now that tangent is like sine. It is an odd function. So it works like this. Oops, this should be cotangent, sorry. All right, so sine and tangent are odd functions. Cosine is an even function. If you forget, which you will, it's fine, just visualize those sinusoids and mentally fold them in half and check to see, do they match up or do they not match up? Okay, that's an easy way to remember that. All right, so there is a new area of functions that we have added to our chart. The next section of a few new identities that we're going to add, and this is the last thing we're going to add. These are called the complementary angles. And this is going to answer a question that a lot of students have from the very beginning when we first do trig functions. And John refers to this topic as the other angle. And you'll see why. All right, let's take a very basic 90-degree triangle. We don't have to put any numbers on it. There's the right angle. Let's call this angle theta. Okay, and then we'll call the sides A, B, and C. Just setting up some basic letters to fill that in. This angle, we know, even if we don't know the number of this, we know that this is going to be 90 degrees minus theta. That's the size of this angle, right? And we call that this angle's complement. And if you remember, way back in geometry land, we said that two angles that add up to 90 degrees are called complementary angles. Two angles that add up to 180 degrees are called supplementary, but the 90-degree pair are called complementary angles. So because we know these two have to add up to 90, and then there's the other 90, that makes 180 for the whole triangle. These two have to add up to 90, so we call this one the complementary angle, right? Or the other angle. There are going to be some cool relationships between these, and we call these the complementary angle identities. And we'll add these to our identities. We'll add these to our list as well, but I want you just to look at them first. The sine of theta, we know, we're here. Sine is opposite over hypotenuse. That's A over C, right? Partnered with that, the cosine of the other angle. So now we're up here. Cosine is adjacent over hypotenuse. Look what happens. We've got the sine of one angle. If we take the cosine, the complement of sine, from the other angle, we get the very same ratio. That's why the words sine and cosine are named the way they are, is because cosine is the complement of sine. Isn't that weird? Just take a second and let your brain sit with that. It works the other way too. If we take the cosine of theta degrees, okay, so now we're back down here, adjacent over hypotenuse, that will be equal to the sine of the other angle. Okay, so now we're going up to the other angle and we're taking sine, which is opposite over hypotenuse, B over C. So these two go together to help us understand the relationship between sine and cosine. They have a relationship when you look at the complementary angles. The CO stands for the complement of sine. Trippy, right? Those names actually do make sense. It also works for tangent, so let's look at that. The tangent of theta, so we're here. Tangent is over Arthur, so A over B. And then the cotangent of the other angle, so now we go up here and we find the tangent of the other angle. It is opposite over adjacent. Oh, no, it should work out. Over Arthur. Cotangent is the opposite of that. it's adjacent over opposite. Right? This is the reciprocal angle. So tangent and cotangent have the same relationship that sine and cosine have. They're complementary in that they're equal when you take the functions of the other angle. The words don't make sense. You just have to look at the way the letters and numbers are going. Similarly, if we take the cotangent of theta, cotangent would be, it would be over Arthur, but it's Arthur over because it's the reciprocal. So it's adjacent over, so it's B over A. Right? And then we find the tangent of the other angle, B over A. So all I'm doing is just comparing the pairs of angles, the function of this one versus the complementary function of the other angle. And this helps us see that this relationship between tangent and cotangent works for the complementary angle too. And then the last one we'll do is secant and cosecant. Secant, and these we get a little bit of turned around. Let me switch to the other page. I'm going to redraw the triangle just so we have it in front of us. This is theta. This is 90 minus theta. Technically, we write it like this, and then we put the degrees out there. I had A, B, and C. And let's just write down our reciprocal functions. Secant is 1 over the cosine, so it is that. And cosecant is 1 over sine, so it's ho. All right, we learned these lesson 41, something like that. But we don't use them as often as we use the main function. So I'm just giving you the letters again so that we can compare. So let's do this. It should be the secant of theta. So secant is hypotenuse over adjacent, C over B. And then the cosecant of the other angle. So now we're up here, and we want hypotenuse over opposite, and it's the very same thing, C over B. And then we do the reverse. We take the cosecant of theta. So now we're here again, and we want cosecant, which is hypotenuse over opposite, C over A. And then the secant of 90 minus theta should be the same thing. We go up here, we want secant, it's hypotenuse over adjacent, it's C over A. So these two prove themselves out as well. And this is secant and cosecant. And the C stands for complementary. Angle identities. All right, that's why the names of the functions are the way that they are. That co does mean something. It partners together two functions that when you compare the function with its partner of the other angle, you get the very same ratio. That will take a bit to soak into your brain, but it's just a really cool pairing and relationship. And now what we're going to do is we're going to add all of that to this page. I already need to flip over. And we're going to need fairly long box because it needs to have 7 rows. 1, 2, 3, 4, 5, 6, 7. I prefer to do the boxes rather than just write lists of these different identities because the boxes help me visualize the information. I'm a very visual person, and so when I'm trying to remember things, I often see them, and the boxes give me a stronger visual image to draw back on. If you are not, let's say you're more of an auditory person, dude, maybe you want to make up like a chant or a song that helps you remember them. Complementary angle identities. All right, and then we can divide it in half. I'm going to give myself a little bit more room on the left because it's longer, but we're dividing in half. So okay, so what we can see is that the sine of theta equals the cosine of 90 minus theta. They each equal this ratio, but we can also say they equal each other, right? We're going to use that in one of our problems. And I'm going to double up this line here to remind me that these two guys have a relationship. Sine and cosine have a relationship. Now we'll get into the tangent. Okay, and similar with this. I'm showing you each function is equal to a ratio, a pair of sides from the triangle, and I'll draw the triangle at the end to remind you of how that looks. But we can also say that the tangent of theta equals the cotangent of 90 minus theta. Okay, we can basically push these two together. Double up here, and then secant and cosecant. Oops, cosecant of the other angle equals the same Okay, so there are the three pairs of complementary angles, and I'll draw the triangle just to remind you of what these A's and B's and C's are all about. This is the angle we call theta. This is the angle that is the complementary, or the other angle, as John calls it. This is 90 minus theta. Technically, we put parentheses around and then we put the degree on the outside. I always blow that off. Okay? And this is called the complementary angle. And then we had A, B, and C. Okay? So if you want to calculate the angles and their complements using the sides, then you can refer to the A, B, and C. If you just want to remember which functions go together, then you know, oh, the sine of theta equals the cosine of 90 minus theta, right? Because you can see these are the same, so these must be the same as well. All right, so these we will use also. All right, is your brain aching? I've given you a lot of information, and now we're ready to practice a few problems. These are called trig identity problems. And there are two simple rules that we use to solve these. They're kind of like proofs, but nowhere near as fussy, and most students think more fun. Trig identity problems, and John refers to this as rules of the game. And I like that because I do think of these trig identity problems as games. When you get to higher, more advanced, either mathematics courses, like I said, calculus, or physics, or engineering type classes where you're applying it to real world problems, you'll find out what these identities can do. For this class, what I highly recommend is think of them as just a fun game. It's just a puzzle. They're the Wordle of numbers. And we're just gonna play them, and they'll get harder as we go, but just think of them as fun little brain teasers. Okay, so what we're gonna do is we're gonna be given an equation, and we're going to change the left side to look like the right. We won't change the right side. We'll leave that side alone, and then we'll do all of our adjusting on the left side. That just makes it easier, and that will help you make sense of the solutions manual too. Whenever possible, we want to change our functions to sine and cosine. We think of sine and cosine as the most basic building blocks of these trig functions. And so whenever possible, we want to simplify and restate things as sine and cosine again, whenever possible. Okay, so these are our two rules. I will remind you of them over and again, but let's puffy cloud those because those are super useful tips. Okay. Now we're ready to actually try one. Are you exhausted? Do you feel like this is the math lesson that will never end? Some of those lessons we did early in the year, they just went on forever, didn't they? I think there are just 2 problems. Now there's 3, but they're short. Example 76.1. Show, the way John writes this is he says show, and then he writes this. He's telling us that the cotangent of x divided by the cosecant of x equals the cosine of x. Well, I mean, you could have fooled me. I didn't know that, but okay, let's say that that's true. So what we're going to do is we're going to leave the right side alone, and we're going to work on restating these functions into some different functions. We're going to try and move them both toward sine and cosine. And hopefully we'll end up with something that looks like this. So what do we remember? Let's see. If we want to take cotangent and restate it as sine and cosine, we've got a tool to do that. Look here in our quotient functions. We said that cotangent is equal to cosine over sine. Oh yeah, we knew this, right? That tangent equals sine over cosine. So this is just the reverse. So let's restate the numerator as the cosine of theta over the sine of theta. And we'll use x, because that's what John is using here. Over the sine of x, okay. And then what about cosecant? Well, let's look at our reciprocal functions. Here we see that, I'll put my shade so it's right in between. The cosecant of theta equals 1 over the sine of theta. Okay, that will help move us toward getting these all into sine or cosine, right? We're achieving our goal of simplifying these. This is the bigger line. Now we have a complex fraction. We've restated this. We've restated this. Now we need to simplify this, and we'll multiply it by the reciprocal of the denominator. Right? This all cancels and goes away. These sine of x's cancel out, And look what we're left with. Cosine of x. The way I show that I'm done is I circle my new simplified version on the left, and then I draw an arrow to show that it matches to what was on the right. Okay? That was the first one. Some students like to write down the equation, or the identity rather, that they're using, which I think is a really good idea. I'll do that on the next one. Here I just wanted to help you focus on the simple layout. 76.2. Ooh, that sun is just creeping on in, isn't it? 76.2. Show, I'm not going to write that, but that's the instruction for a trig identity problem. Sine of x times the cotangent of x equals 1 over the secant of x. Okay, again, we're going to leave this side alone, and we're going to put this into sine and cosine as much as we can and see if we can get it to look like that. Okay, sine of x, I like this part. I don't want to change it. Cotangent, I would rather restate that as sine and cosine. So let's look at our page and see what we've got. It's cotangent. This one looks like it would be a good choice for us again, doesn't it? Because it will put things into sine, cosine and sine. So if you like, you can write cotangent of x equals put this in a little puffy cloud, so I know that's the tool you're using. So then we'll rewrite it as sine of x, that's the first part, times cosine of x over the sine of x. Sometimes students like to put a 1 underneath there to just kind of get their bearings and keep the fractions neat. Beautiful. Now all our basic rules of algebra are going to apply unless I tell you differently. These cancel. We can cancel just like we do anything. So now what we're left with on this side is cosine of x, but that's not quite right. But we also know, if we look at this, that the cosine of theta equals 1 over the secant of theta. Okay? Now you know why I went to the trouble to write things out twice, because when everything is going on in these identity problems and your head is kind of running in circles, it's nice to have it laid out exactly the way you want to see it and not have to try to take something like this and make algebra happen in your brain. It's nice to just have it written out. So we've got cosine. We can write it as 1 over secant. And this is an identity in and of itself. So I'm just going to puffy cloud of knowledge that. There's the 1 over the secant of x that we wanted. So now they match and we're done. Oh, right? The way that you write down your steps is fairly fluid. All right, there isn't a super conventional one way to write the steps. Write down as much as you need to remember how you did it, right? If you come back and look at this in 2 days, I want you to be able to explain to me, oh, let's see, I used this identity to change cotangent. Oh, and then I used this identity to change that into 1 over secant. You have to be able to follow your own thoughts and remember your thinking. Write down enough so that you can. One more. That's a harsh shadow. I hope you can see. 76.3. One more identity. Show cosine of minus theta. Oh, so we have a negative angle identity times the sine and now we have a complementary angle equals cosine squared theta. Oh, a square. That's kind of weird. All right, let's go through these one by one and see if we can simplify these two expressions. The first one is going to be in our negative / even odd functions. The cosine of negative theta, okay, we see that that's just cosine of theta, right? Yeah, because negative 90 equals 90. It's an even function, blah, blah, blah. So we can use this, cosine of negative theta equals, okay, so we'll change this part to the cosine of theta, and then let me double underline this one so we can see where our two parts came from, right? Here's where the first part changed. Now we need to look at the complementary angles. The sine of 90 minus theta, the sine of 90 minus theta equals the cosine of theta. So we can rewrite this as this. This is what we're going for. Now we see we're multiplying the cosine of theta times the cosine of theta. Oh, well that's just cosine squared theta when we do that multiplication. And there's our answer. And I do smiley faces. Where you put your star or your smiley face, I just put it somewhere up here. All right, I didn't do that on my other ones, did I? I better go back. There. And here. Okay, so you now have lots of information, more than enough to be dangerous. This sheet will become your best friend. We will add more to it. This is why I wanted you to do this on a separate page, because you do not want to be flipping back and forth through your notes. You want to have a separate page with all this stuff written down so you can keep it handy and keep looking at the front and the back of it. There will be more pages as we go. Not a lot more. We have about half of the trig functions that we will learn already written down. We will be doing these trig identity problems for a while, so be patient with yourself. And I'll talk more about this later, but the goal is to memorize this. And I realize that probably feels a bit overwhelming, but there's a lot of logic and common sense that we can find to help us remember the parallels here. For example, in these complementary angle functions, the names help us know which pairs go together, right? Sine and cosine, tangent and cotangent, secant and cosecant. So we're not just memorizing blind information. We'll talk more about it as we go. For now, go rest your brain and then give yourself 15 minutes to walk around your neighborhood or feed the chickens or do something to rest your brain, and then dive into this homework and see if you can make sense of these new problems. Goodbye.